All right, hey everyone, welcome back to another live stream from Sourcegraph. Oh, sorry, got an audio thing going there. Welcome back to another Sourcegraph live stream. Today we're here with Andrei Vasnetsov. He's the CTO and co-founder of Qdrant, a scalable vector database that you can use for nearest neighbor search for all sorts of vector applications, but probably most top of mind would be kind of like embedding search. If you're trying to build some sort of semantic search off the latest and greatest large language model or machine learning model, you're going to have these large vectors that represent your bits of data that you want to retrieve, and vector databases are here to solve that problem at scale. So, Andre, thanks for joining us today.
Thanks for having me. Nice to meet. Nice to be
Cool.
here.
Yeah, it's great to have you. I feel like vector databases are all the rage right now. You're kind of riding the wave of the latest AI revolution. There's tons of potential here for building cool applications, including stuff that Sourcegraph is working on to develop semantic search. So we are looking at you and a bunch of other vector databases as kind of candidates for how we can scale our own semantic search backend. But before we get into all that, I feel like we have an audience that may be a bit newer to this space. So can we start out by talking about what the kind of applications of vector databases are?
Yeah. So usually when you speak about search, you imagine something like Google when you type keywords, some phrases, and it will return you a result in the form of list of documents.
Yep.
And that's a typical application of search, but it's not the only application of search. And even the keyword search was used in a lot of very different applications. It was
Yep.
used for recommendations. It was used for auto completion. It was used for semantic search as well, right?
Yep.
And for code search, it was like, of course, there are search engines which does search over code, even with all the technologies like keywords. So vector search is fundamentally different
Yep.
from keywords, and instead of using this words or phrases, it uses an embedded representation of objects. And objects could be basically anything. It could be a piece of text, it could be a word, it could be a picture, it could be even a history of user actions. And
Yep.
the only thing you need to make it work is some form of model which translates your object into this vector representation. And the vector representation have very interesting property
Mm-hmm.
provided by the model is that if you have closed vectors in some vector space,
Mm-hmm.
then those objects are similar in some form. It could be semantic similarity, so two sentences or two pieces of code are
Yep.
doing something similar or mean something similar, or it could be visual similarity as in case of images. Those usually is defined by the model you are using.
Yep.
And based on this model and based on similarity, you introduced this model, you can build different types of applications. You can build visual search where you can find similar images, or you can build a application where you find similar pieces of code which is doing similar type of actions.
Yep. So basically, this is kind of like game-changing technology for search. Like when people traditionally think of web search, it's like keyword-based, where you can kind of like intuitively, okay, if I search for, I don't know, like developer tools, you might,
Yeah.
apply some stemming to that and come up with like develop and tools, and then just do a very simple keyword match. You build a reverse index and surface documents that contain the words develop and tools, and then apply some ranking. But now it's kind of changed where like you map the phrase developer tools to some very high dimensional vector space. So you get a long list of numbers that captures some sense of like the semantic meaning of those words. And
It's not
then,
not that large. It's usually a couple of hundred, but it's
Okay, cool.
actually very dense. Like information is very compressed in this vector,
Yeah.
and that's why we don't usually even know which meaning each dimension has. So
Yeah.
we can only observe overall properties of the whole vector.
Yes, and this is something that's learned from the data. Basically,
Yes.
these models
Yeah.
are designed to predict, they're designed to learn the structure of the language so that they can predict, the next words that will come in a sentence or something. But as almost like a side effect, you get this nice representation of the data, such that, like, if I mapped, the phrase developer tools to the embedding space, this list of 100 numbers or so, and then I mapped, a related term like I don't know, coding or programmer, you would expect those numbers to be close to the numbers in developer tools, even though they don't have any actual like keyword similarity, right?
Yeah, yes, that's a typical task for language models when they predict a next word in the sentence or masked word in the sentence, but it's usually not a final task for
Mm-hmm.
this encoders model. So it's good. It works good for individual words, and you have models like word2vec or fast text,
Yep.
also a form of text embeddings.
Yep.
But if you want to have a vector, a good vector over a whole sentence, you usually need to match whole sentences as well.
Right.
So usually what researchers do, they take a good foundational models like language model, and then
Yep.
they train it on downstream task. Like information retrieval is one of them,
Yep.
and and for this task, they have special data set which contains like special types of documents, like query document and
Yep.
the one which you want to find.
Yeah, you basically take a starter language model that's been trained a lot of data that has good understanding of the structure of the data, and then you take a data set where you're saying like, okay, now I want you to explicitly optimize for mapping these nearby terms to each
Yeah.
other in vector space, and that has the effect of moving the model parameters more to be better for your application. Because if you just take the embeddings out of GPT-3 or
Yeah,
BERT right
it
away, they
doesn't
might not
work at
actually
all.
be that good for the semantic comparison.
Exactly, exactly.
Okay,
So
cool.
usually, if you want a good retrieval, you might want to use specialized model. It might be
Yep.
based on BERT or
Yep.
GPT, but at the end, it's still a bit different. At the end,
Yep. Okay, so you kind of fine tune your model using Hugging Face or maybe OpenAI. Now you have this thing that you can use to map strings of text or maybe images or some piece of data to embedding space. So this list of hundreds of numbers. Now you're not done yet, right? Because now that you have these vectors, you need a way to efficiently search them.
yeah,
So like linear scanning only scales so far. Like that's kind of like the naive approach. Is just like you have all your vectors representing all the documents in your search index, and then you just scan through all of them. You take the vector dot product, which is just computing the distance to each of them, compare them against the user query, and then you find the closest one. Obviously, that doesn't scale. If you want to index a much larger code base, you need a scalable indexing strategy, and that's where you come in, right? You are
yeah.
a vector database. You allow me to scale to many, many, many like huge corpuses.
Well, actually, there's a step in the middle. How people usually approach this problem before vector
Mm-hmm.
databases is the usage of libraries.
Yep.
Libraries like FAIS, like NMSLib. It's similar to, for example, Lucene, Apache Lucene. It's
Lucene,
index.
or yeah.
Yeah, Lucene.
Yep.
It's a library used in, for example, Elasticsearch to make reverse index, so you can apply your full text
Yep.
um, queries to some index data. And
Yep.
from this point of view, vector databases are same to Apache Lucene as
Mm-hmm.
FAIS or other libraries to vector database. So at the end, we are maybe not built on top of them,
Mm-hmm.
but we are a natural extension of this concept. So if you are working with some embedded environment, or you are making experiments which only needs to be run on local machine, then it's fine, of course, to use
Yep.
libraries. But when you use to production, you need a very different set of features.
Yep.
You need scalability. You need concurrent access from multiple locations. You need fault tolerance. So if your machine goes down, you don't lose your functionality on your web
Yeah.
service, and so on. So that's where vector databases come in play.
Okay, so if I'm building an AI search engine, my initial prototype, I'll probably just do like a linear in-memory scan across all the vectors, and the next level up is using something like FICE or like a library that does maybe
Yes.
some like basic clustering or whatnot. And then the next level after that would be to use a vector database. Once I want to
Yeah.
deploy into production, I want to scale it out, I want it to be robust and reliable, et cetera, et
Yes,
cetera.
yes. Of course, if you are thinking about production application right away, you can skip the step with libraries, as
Yep.
you usually skip listen in and go right away into
Right.
Elasticsearch if you need full text. Because in many cases, it's just easier to use something with ready-made API, something which works out of the box. And
Cool. Before we dive into kind of like the technical weeds here, I know that you all have built some demos on your site that feature Qdrant as kind of the search backend. Do you want to show off a bit of that?
Yeah, so we played around with semantic code search on our own, and we built a demo application which shows uh, how it can be utilized
Mm-hmm.
using Qdrant, and we indexed our own code base into it, and yeah, basically prepared this pretty simple demo.
Yep.
Um, it's actually available online. Everybody can just reach this website and play around with it. And the main challenge was actually that there are no ready-made encoders for Rust, and Quadrant is written in Rust. And
Hmm.
initially, we thought that it would be a problem, but it turns out that actually most of the meaning in the code is lying within names of variables or names of functions and
Yep.
so on. So at the end, even models trained for other languages work pretty fine with Quadrant,
Nice.
Quadrant source code, with Rust. That's the first observation from our side.
Cool.
Second observation is that actually there are two parts which you might be interested in searching in source code. The first
Yep.
part is code pieces itself, like a body of functions, body of loops, body of if statements, some sequence of operations
Mm-hmm.
is the first one. And the second one is actually the definitions of function. So
Mm-hmm.
if you are working in some form of IDE, you might usually need to search someplace in the code. And for example, JetBrains provides you functionality to do keyword-based search, and even in the code base of quadrant size, it's already not enough to have just keyword search, because even I do not remember how I name some functions.
Mm-hmm.
I can imagine how it could be named, but I cannot remember the exact
Yep.
phrase, the exact words I use. In this case, semantic search is actually pretty helpful.
Cool.
You can even use some regular models, like not especially designed for code, but just for general texts.
Yep.
And that's actually what we did. We combined both of these models. So at the same time, we query the one model which is responsible for pieces of code, and the other model responsible for definitions of functions. And we join,
Me
we
clarify
merge.
that a little bit. You have one model that's trained, or one model that's trained on like function bodies, and then the other one that's trained on what files?
The other model is just trained on text. We just took a model
Okay.
which is general purpose for semantic search, and
Okay.
we indexed only the definitions of functions into
I
the
see.
second text-based model.
I
So as
see.
a result, we have a function, a search process which queries both types of indexes
Yep.
and then merges it. And you can see that in this case, we can search for both functions and places inside the function which is
Yep.
responsible for a query. I guess on the third example is the most relevant one. So we have
Mm-hmm.
a function which does flush of data, and
Okay.
inside this function we can highlight the piece of code which is responsible for flushing of write ahead lock.
Yeah. Yeah. Does this engine index any other code bases? Like, could we have it index like Sourcegraph's repository or something like that?
Yeah, for this demo we only index Qdrant, but
Okay. Got it.
the code for this demo is open source. You can of course use it further.
Can you search for something like I don't know, like search API? Let's say like I'm completely new to this code base, and so the first thing I would want to find is like the entry point to the API. Okay, cool.
It's
So that's in points API file. Is that kind of like the main
Yeah,
like
Tonic
handler?
Tonic Tonic is a gRPC server.
Oh,
So
okay,
inside the
cool.
gRPC server, you have a search endpoint.
Okay, what if I want to find the place in code where you construct the or update the index? Like maybe I would search for like update vector index or something like that.
Yeah, let's try that.
Update
So
vector. Okay, cool.
yeah,
So that's updating one segment in presumably your index.
yeah.
Is that the thing that you would say is the thing to look for?
I would say that we do not update a vector index on its own. So
Hmm.
our architecture is a bit different. So we have
Got it.
immutable indexes, and we only merge them between.
Yep. Cool. So the second result looks interesting too because that looks relevant, but it doesn't look like it actually has the word update. It's just upsert, and like the
Yeah,
model is able to capture the semantic similarity between those two terms to
yeah,
bump
exactly.
this.
So
Yep. Yep. Yep.
that's a benefit of semantic search is that you do not need to know exact words you used in naming functions, but it's
Yeah.
enough to. Uh, yeah, one downside of the semantic search is that there is no way to tell if two pieces of code are not similar. So point
Mm,
of um, from point of view of this vector space, uh, all vectors are somewhat similar to all other vectors. You can define some thresholds,
right.
but those thresholds are up to application. So we cannot infer those thresholds on the server side.
Right. So if you search for something like I don't know, like rainbow ponies or something, it will
Yes,
generate
it will
results.
find something. Yes, rainbow.
Yeah, let's see what is semantically similar. Init.
Yeah,
Interesting.
some very strange things. It's
Sorry,
completely not relevant, but it's still a search result.
quick
You
question.
will see.
You said that there's like two indexes backing this, and they're both vector indexes. Is that right? Can
Yeah,
you describe what's the difference between those two again?
yeah, they are in the different parts of code and with
Okay.
different models. The first index is just function names
Yep.
encoded with the general purpose model, and
Ah,
the
okay.
second index is
Bodies.
pieces of bodies,
Yep.
not even bodies, but
Oh, like
foldable pieces of
sliding
code.
windows. Folds. Okay, so you do like blocks or
Yes,
okay,
yes,
got it.
and we encoded with model specialized, like trained on code.
Ah, I see.
So
Okay,
and you can
cool.
see that there is no highlights in this snippet, and
Yep.
that means that there are no overlap between two search results. So it will only demonstrate now the result of first semantic model and not the code model. And if you go to some other examples, you will see that there is an overlap in two results.
Okay, cool. Yeah,
So
I guess like
that's actually how you can filter
Yep.
out bad results. That's one of the
Yeah,
approaches.
that's neat. It's like you get I guess like do both models get incorporated in the like result ranking, or do you rank by the first one and then select the snippets with the second one?
Yeah, we do the second approach. Yes,
Okay. Okay.
we sort by semantic, and then um,
I see.
yeah, we rank by second one.
Okay, super cool. All right, so basically everything we've talked about up till now, which is like the process of like generating the embeddings and all that, it's kind of well, I guess we talked about like the two vector databases, but I want to dive into the kind of specifics here. So like once you have these models and you have these vectors that you want to index, now you want to put them into a vector database that can respond with like, okay, here's a novel query. Let me map that to a vector and let me find you the nearest vectors in my database that are closest to the thing that you just submitted.
Yeah,
Can you tell us a little bit about how a vector database works?
yeah. So in our example, we do two models and for two vectors from the same request,
Mm-hmm.
but overall approach is same. So once you have vector, you can go and to the vector database and use this vector to search for the closest one. And we are using some modified version of HNSW, which is pretty common and performant index for vector data.
Mm-hmm.
On top of just searching for closest vectors, you might also want to have some restrictions on the area of search. So for example, if you have like 1,000 indexed repositories and
Mm-hmm.
you only want to search within one of them, you
Mm-hmm.
might need to want to apply filters uh, on your search. And and that's what actually make Qudrant unique compared to
Okay.
all other databases,
Yep.
as we uh, especially designed from the day one to support this type of combination efficiently, to support uh, filtering at the same time as you do similarity search with HNSW.
Interesting. Okay, so walk me through that a little bit. I'm not sure I quite understood.
Yep.
So like, maybe like take a step back a bit. So at a basic level, it's like okay, uh, I could just do linear scan.
Yes.
That's going to be O of n in the size of my corpus. You know, at
Yes.
some point, there's going to be enough documents where I like, you know, that's not, it's going to take too long. And
Yes.
then I think most vector databases, my understanding is that there's some sort of clustering. Like you try to build some sort of tree where you kind of group. Uh,
In case of HNSW, it's a graph.
it's a graph. Okay.
Yes, it's a graph, and each node of the graph contains links to somewhat similar neighbors. So basically,
Ah, I see.
the process of building this graph is similar to searching. So you start with one
Yep.
node, then you add the next node, and you make a link between those two first nodes if they're close enough. And for the first two, it's always the case. You
Yep.
always link the first two. Then you add another bunch, and at some point, if you need to add a new node into the graph, you need to search for the closest nodes, and then create links between those closed nodes. There are some additional like tricks into this process which make it more robust, but I guess we can ignore it for now, just for understanding for our listeners. Uh,
Yeah.
so the main idea is that you have a graph, and this graph connects close nodes to each other. And
Got it.
the search process in this graph is actually depth first search. You start from one node and you go in the direction of the closest.
I see. Okay, so that's interesting. So basically, at a high level, it's like, okay, let's say I start with one vector, and now I want to add a new vector to the database. It's like, okay, there's one vector, and I'm going to search for the nearest neighbor. That's trivial. It's just the
Yes.
one, and then maybe I add another node to the graph, and there's an edge from my first vector to my second vector, or maybe they're both at the root. I don't know. At some point, I end up with like a bunch of vectors surrounding the root node, and then when I add a new vector, I compare it
Yep.
against the root node, and then I compare it to each of its, I guess, adjacent nodes, and then I walk in the direction of the closest neighbor. Is that right?
Well, you do not need to connect all to the root node.
Okay.
You select the closest one, and
Yep.
usually it's a fixed amount of neighbors for each node.
Yep.
And you start with the root node, and from the root node you move into the direction of the node which is closer than root.
I see.
Yeah, so
Got
it's
it.
like a greedy search,
Got it.
greedy search type of process.
So I imagine if you implement this naively, at some point you might lose the guarantee of finding the nearest neighbor, right? Because if you're doing a greedy search, maybe you go down a path where there's
Yes.
actually a vector down some other path that you didn't explore that's actually closer. Are there like constraints that you impose at index time to ensure
Yeah.
that you maintain the property that you'll always find the nearest neighbor, or is that just like kind of naturally fuzzy? Like you might not always find the nearest neighbor. You
Yeah,
just
yeah.
have a good chance.
First of all, there is no guarantee that you're going to find the best, the closest nearest neighbors. That's why
Got
it's
it.
an approximate search.
Yep.
But the probability is high now. The
Okay.
problem is that if you apply filters in this process, you are significantly decrease the probability of good result
I see.
because you randomly take away some nodes if they don't fit the filter, and
Interesting.
you don't want to search through them. You need to exclude them from this greedy search process, and that's how you can end up with pretty bad results if
I
you
see.
do it naively.
Okay, so a
And
filter in this case, is that just like a traditional search filter? Like I want results in this language or
yes, yes,
in this
yes,
repository? Okay, got it, got it,
yes,
got it.
yes. Yes, and there are a lot of different applications which require these filters. For example, location-based filters are very common in all kind of e-commerce applications. Even like
Yep.
you probably want to order food from restaurant which is nearby, and
Yep.
not from the restaurant which is in another country or
Got it.
something like this.
We have a question from the audience here. Do you see vector searches or vector databases, I should say, incorporated into traditional databases? Like a Mongo or MySQL. I know, like Postgres has
Yeah.
like a PG vector extension now.
Yeah, yes. Yes, same as Postgres have support for full text search.
Yep.
At the same time, you're still going to use specialized solution if you want best performance and best experience. So yeah, of course, it's possible to integrate vector search into basically any database. For example, also the ClickHouse implemented
Yep.
this vector search. And yeah, if you are a user of ClickHouse, if the ClickHouse functionality is important to you, then you can use vector search inside ClickHouse. But if you are building something which is like the main function of which is a
Yep.
vector search, then you should probably consider alternatives where vector search is a number one citizen.
Yeah. Makes total sense. Um, Okay, cool. So you were saying that one of the key points of differentiation for Qdrant is your ability to do filtering and nearest neighbor search efficiently. Like that's something that
That was our original idea why we started to build Qdrant in the first place.
got it. Can you talk a little bit about your algorithm or approach? Like how,
Yeah,
like you said,
sure.
like as you're filtering along the way, oop,
So, sorry.
you're kind of like pruning things. and that affects the like quality of results. I guess like naively, I could just say like, okay, I'm not going to implement filtering in the database. I'm just going to use the database to over select all the results, and then I'm going to like filter after I get all the results. I
Yeah.
could just fetch a lot of results from the database and then filter after the fact. Like why not do that?
Yes, it's gonna work unless your search result, like your filters, is correlated to semantic you are using.
Yes.
And like, if it's a case, you are gonna need to retrieve a very huge pre-selection
Got it.
for a correct results.
Okay, so then do you incorporate like the filtering criterion into the graph that you're building then? Or
Yes, yes,
okay.
yes. First of all, it's integration between graph and um, payload you store along, like
Yep.
this filtering parameters.
Yep.
Second of all, it's a modification of graph itself to avoid this problem of disconnected graph. So
Yep.
the problem is that if you filter too much, your graph become disconnected and you will get bad results. And we are avoiding this problem by basically introducing additional extra links
Yep.
uh, to this graph, which is derived from the payload you have. So that's main architectural property of Qdrant is that payload is stored very closely to vectors. And vector index depends not only on vectors themselves, but also it depends on payload you upload along.
Interesting. The
By
payload.
payload, I mean some kind of metadata, like this additional
Ah, I see.
information.
Okay, got it. So you store the payload information alongside the vectors so that you can take that into account when you're walking the graph.
Yes, yes.
Okay, very cool. And then does the payload also inform like the structure of the graph, like what
Yeah.
nodes that you? Okay.
Yeah. So
Okay, got it.
if you index, if you create additional index in payload, let's say by some keywords, this information about keywords will be used to create additional links in HNSW graph, and this
Yeah.
graph will not become disconnected if you apply same filters.
Yep. Got it. Okay, so one of the nice things about Quadrant is that it's open source. Can you talk a bit about the decision to make the code open source and what sort of abilities that unlocks? I mean, I certainly think it makes it very attractive from Sourcegraph's point of view. A lot of our customers are self-hosted, so we can't necessarily use a
Yeah.
cloud-hosted proprietary only vector database. But can you
Yeah.
talk about your calculus in doing that as a business?
Yeah, I basically started as a pet project. So
Ah,
it was
nice.
it was like a default decision for me. I just
What were you
wanted to.
building originally, or like what was the
Yeah,
impetus for starting that pet
yeah.
project?
Originally, I worked on several projects which involved search, and we
Hmm.
were experimenting with vectors as well. It was a very big deal for us because we had very dirty data sets, which very dirty and very small number of keywords. So
Yep.
you can imagine that keywords are not very good uh,
Yep.
for this type of purpose, and also we had this additional requirement to display everything on map, and it was basically a e-commerce project, and
Got it.
we used a lot of filtering and maps, and we built prototype initially with just vector search without
Yep.
filters. It was quite good. We had no problems we faced before with
Yeah.
keywords, but we could not actually deploy it in production because these libraries which existed at the time, they just didn't support any kind of filtering, any kind of this additional um, logic you might want to apply on top of
Yep.
filters. So so we ended up with just some custom Elasticsearch setup, which didn't work really great.
Yep.
After that, I switched to another project, was HR related, like a job board type
Okay.
of application, and again I faced same problems. Um, uh, on top of similarity between different professions, we had a lot of requirements like location of candidate again, um, some experience requirements, some
Yep.
country, and so on. All of
Yep.
these filters just didn't work with existing solutions. So basically start building Qdrant to solve my problems at work. And
Nice.
apparently I'm not the only one who's having these problems.
Cool. Can I ask you about embeddings a little bit? I know this is a little bit outside the database
Sure.
itself, but I think a lot of people working in this space have questions about, which models yield the best embeddings? What are the good starting points? Should you use one of the open source models, or should you go the proprietary route with OpenAI or anything like that? Like, which models are you using to generate embeddings, and like what's your approach? Are you going
Yeah,
open source? Yeah.
in our demo, we almost always use models from sentence transformers library. It's open
Like
source.
SBERT or something like
Yes,
that.
as
Okay,
Bird, exactly.
cool.
They have a pretty nice collection of ready-made transformers.
Yep,
And for multimodal encodings, we usually just use clip. It also
yep,
have pretty good performance out of the box.
yep,
And for like if you want to boost your accuracy in some specific domain,
yep,
we usually recommend to do a fine tuning, like
yep,
collect
yep.
some amount of data. We also have this second project of ours, which is like a side biz. It's called Quaterion. It's a framework for fine tuning
Sweet.
neural encoders. And the main idea of this project was to make this process of fine tuning as simple as possible in terms of resources requirements. So
Yep,
imagine if you have a large neural network like BERT, and you only have 1,000 label samples in your specific domain, you probably won't be able to fine tune the whole network.
yep,
You only have enough data to update a small portion of parameters.
yep,
And in this case, Quaterion might be a good choice for you because it have a lot of optimization, so you do not need even to infer the whole model in the training loop. You only need to like pre-encode the training set, and
yep,
then the training loop itself will use basically a cache of vectors and
yep,
only update a small portion of parameters. And you can
yep.
even fine tune BERT models on a laptop even without GPU. So that's the main idea of the
Oh
project.
wow. I'm surprised that the fine tuning on a laptop is fast enough. But I
Yes,
guess it.
yes, it is because you do not evaluate the large model. You only update small portion of weights, and you can
Okay, yeah,
boost your performance on some downstream tasks up to
yeah.
like 10% accuracy
Oh, that's awesome.
with minimal efforts. Like you only need like thousands of trained samples.
Okay, cool. I want to dive into the source code a little bit, but before that, we have a question from a very eager
Sure.
listener who's asking like if you have any plans to integrate with other databases. I think the idea here being their production data is already in these other databases, and they don't want to build like a pipeline to another database. Do you expect that you'll integrate with other databases at any point, or is Quadrant
This is a question for
standalone?
other databases, I guess. Like usually a production environment, you split like you have a single source of truth, could be a
Yep.
Postgres or MongoDB, a proper like transactional database, and
Yep.
then you have a bunch of services like indexers,
Yep.
which consume updates from some um, uh, queue provider,
Yep.
and then yeah, you kind of split this into different services.
Yep.
So from my perspective, this approach is preferable.
Cool. Awesome. Should we dive into the code a little bit?
Sure. Let's do this. Yeah, I prepared it. It up is my
Nice. Thank you.
source graph. So yeah, as I said, Qdrant is written in Rust. It was actually pretty. I'm satisfied with the choice of language. Actually, it was actually my first project in Rust.
What
Turns
would have
out,
been the other language? Like, what was the other candidate?
so I was considering Go.
Uh huh.
I was considering Scala
Mm-hmm.
because I had some experience with Scala, but yeah, apparently it's not really great because you have this GVM dependency with
Yep.
you, and it's not exactly fastest fastest language.
Yeah,
So
that's some
uh,
runtime overhead.
yes, it's huge runtime overhead, and not only runtime but also garbage collection, which just
Mm.
basically stops your application
Yep.
until it's done. Uh, yeah, the main choice was between Go and Rust,
Mm-hmm.
and I decided in favor of Rust because uh, it it is advertised as a system programming language, and
Yep.
by system it means that it's used to create tools used by other programs, and
Yep.
that's exactly the definition of the search engine.
Yep.
It's something which is used by other other backends, and so on. So this
Yep.
was the choice, and actually I'm satisfied because it helped a lot. Like the compiler found so many potential mistakes, so
Yep.
that if I were using any other language, I would still catching them every second run.
That's awesome. That's a great advertisement for Rust. It lives up to the hype.
Yes. So Rust is I guess one of the best architectural decisions I made in
Cool.
Quadrant. Uh, yeah. So speaking about
Awesome.
architecture, I guess, do you have any kind of questions for me,
Yeah,
or
so
I can?
I think typically what we like to do with these code deep dives is to kind of like trace through maybe like a life of a query, or in this case maybe like what happens at index time. Like when I submit a new vector to be indexed in the database, maybe starting at like the API level and then kind of like drilling down all the way to the part where it's writing to disk. Just like
Yes.
walk us through, like trace us through that call and response cycle.
So sure. Yeah. Everything starts with the API, and Quadrant actually supports two types of
Yeah.
API. It's REST.
Okay.
I'm not sure if it's a full source code, or
Should be. It's
should be
lib
more.
API source.
Okay. So yeah, maybe we can start with a bit different directory then. If we go to yes, so yeah. So we support REST API served by Actix,
Mm-hmm.
and gRPC API served by Tonic. The idea in this support for both protocols is that usually if you want to debug something, you go to REST API. It's easy
Okay.
to look up something in just browser without
Yep.
any external tools.
Yep.
But if you want performance, if you actually care about like this latency within your system, you probably want to go with gRPC. It's
Mm-hmm.
structured a bit differently. So Actix and REST API looks good for developers, and gRPC looks good for machine. So machine
Yeah.
can parse it faster.
Makes sense.
But except for this, there are no actual differences in API. You can do almost everything in the same way with both APIs.
Okay. Can you show us
Uh,
like the gRPC handler and maybe zoom in a little bit too? I think that might be. Yeah, that's great.
so we have all pretty much auto-generated from protobuf definitions.
Okay. Cool.
Uh, we have this point API is the most interesting one. So here you can observe, you can delete, you can set payload, you can overwrite payload, delete
Cool.
payload, clear payload, like all the different cases. and also you can create indexes for payload.
Got
Also, we care most about performance, so we also have API for batch search, and the API for insertion is also
Cool.
batch API by default. So if you have a case where you need to make multiple queries at the same time, you don't need to introduce this overhead into your processes. You just make one query and get multiple results with a single shot. I'm
Got
not
it.
sure if I can walk the usages here.
It seems like we're having some trouble with our go to definition index right now. But if you
Yeah,
want us to
okay.
just search for, you could use the search bar. So if you just search for upsert in this repository.
There will be a lot of them.
How
Okay.
about something like more distinct, like that search underscore batch function?
Method search. Yeah, okay. Let's go there. Yeah, nice. So after API, like API is abstracted away from actual objects which manage the storage.
Yeah.
And in this case, we call it like table of content.
Mm-hmm.
Table of content contains information about all collections you created in Qdrant. And
Okay.
each collection is basically independent entity. So
Yep.
each collection can have vectors independently from all other, like different shape of vectors, different distance metrics, different payload. It's basically
Yep.
the same as in Elasticsearch, where you have indexes. I think it's called
Yep.
indexes. Inside the collection, like user should only care about collections, but inside the collection, you also have shards, and inside shards you have segments.
Mm-hmm.
And those are abstractions for managing first the distributed deployment and second the indexes themselves.
Mm-hmm.
So our concept is following. So each shard have a non-overlapping set of points, and when you upload some point, it goes to one of the shards defined by some hashing process.
Okay.
So it takes an ID, apply hashes, and define the ID of the shard. And inside the shard, there are multiple segments, and each segment, I guess I can open now different. Yeah, so
Cool.
there is
Oh,
a
no,
storage. There is a storage. After storage, there is a collection, and
okay.
after collection, there's a segment.
Okay. And each layer is the hashing. The hashing must be like distance sensitive. Is
No,
that
no,
right?
no,
Or
no.
oh, sorry,
It's just
you did
for balancing. Yes.
got it. So like the search request will fan out to all shards.
Yeah.
Like when you do a query, it's gonna forward that query to all shards and do the search within each shard, and then there's gonna be kind of like a scatter
Yeah.
gather step.
And then you can replicate shards, so you can
Okay.
can
Got
have
it. Got it. Got it.
multiple instances of one shard.
Yep.
Um, yeah. So inside collection, there are actually a bunch of files. Inside collection, we have shards, and there are multiple types of shards as well. So we're trying to follow this pattern where we have the same interface for shards which are located on one machine and shards which are located into remote machines. So at the end, you can query any machine in your cluster, and it will give you the same search result. It will find the path to the proper machine, like automatically under the hood.
Cool. And then can we pop into like within a shard, it has multiple segments. How does it choose which segment to
Yeah. Segments are chosen randomly
okay.
mostly, and segments are used um, to be able to index data independently from the upload process. So when you start to upload your records,
Yep.
uh, it will first create unindexed segments, just plain full scan, as you mentioned before.
Right, right.
It scales up to some extent, and even faster. It even works faster than something with HNSW. So
Yep.
if your collection, let's say, smaller than 10,000 vectors, it's just faster and simpler to do a full scan over this collection.
Yep.
But when you uploaded more than this amount, it already makes sense to create index segments. And that's a job of optimizer, which will go and find those segments which
I see.
satisfy the optimization conditions. It's configurable parameters, but the idea is that if segment is large enough and it still doesn't have index, it's time to build a new segment with index
I
for
see.
it. And when you build segment, you need to care about access to your data. So
Mm-hmm.
the process of updating needs read access, and it might become a problem if user wants to update the same segment with some new vectors or new payload.
Mm-hmm.
And in our case, it's handled with copy on write mechanism. So
Mm.
if you make this request during optimization, it
Yep.
will basically mark some records as removed in one segment and copy them into a new one. So from user, it will be completely transparent.
Mm-hmm.
You will see your updated results. It will search everything properly, but under
Mm-hmm.
the hood, those records will be just moved from one segment to another,
I
and
see.
yeah, no data will be lost. So it's all this complexity is to make experience of the developer transparent. So you do not need to
Yep.
wait for index to complete. Do not need to explicitly load some segments in memory, mark
Yep.
them as done, or anything like this. You just work with Qdrant as a regular database, make your requests, and get results.
Yep. Makes total sense. Um, so question here. So within a shard, if I do a search within that shard, does that consult every segment? You said that the segments are
Yeah,
kind of
yeah,
chosen
yeah.
randomly. So that implies like
It's
segments are roughly analogous to shards
Yes,
within the shard,
yes,
right?
yeah,
Okay,
yeah. So
got
the
it.
difference is that shards have non-overlapping points, and but segments can have overlaps, and
Ah, I see.
those overlaps are resolved during the search time.
Okay, very cool. So basically, the only part where the like an HNSW style index is implemented is within the segment. So
Yes,
up until that, it's all just like you're kind of like
yeah,
distributing the
yeah.
computational load.
Management, yes. So all the indexing happens within segment. Yes,
Yep.
and we have
Cool.
yeah
Can you talk a
HNSW
little bit
indexing.
about the HNSW implementation? Like, are there any kind of like tips or tricks that you employed to make that fast?
Yeah. So first of all, we re-implemented basically all tricks and heuristics from the original library. Um,
Mm-hmm.
there are a bunch of them.
Yep.
Second of all, our approach is that we build index and make it immutable. So we already know all the statistics required for optimal graph during the optimization.
Okay.
So with this approach, it's possible to uh, make very compact, very optimal segments, even with constantly updating collection. So even if you remove and add new points, uh, each segment is optimal on its own.
Okay.
That's actually a big deal, especially if you want to build something like quantization in the index, or if you want to build HNSW to work on disk, for example. Because if you want to make it on disk, then you have a very um, tightly packed data structure,
Yep.
and this data structure could only be efficient if it's immutable.
Got it. Okay, cool. Is there like a reference documentation that you'd recommend if someone wants to learn about HNSW, by the way, stands for Hierarchical Navigable Small Worlds. It's basically
Yeah,
the
yeah,
name for the index type that underlies this kind of like graph-based approach
yeah,
to
yeah.
finding nearest neighbors.
If you want to learn about HNSW itself, I guess the best source is the original paper. Uh,
Cool. Is that on like archive?
yeah.
Okay.
As I
Efficient and
remember,
robust nearest neighbor search using hierarchical navigable small world graphs
yeah, by
by
Yuri
Malkov.
Mikl.
Yeah,
Yes,
Mikov and Yashunin. Okay, cool.
yes. So that's an original paper. It have explanation of the general approach. Uh, if you want to learn more about the problem of filtering associated with HNSW, you can find our um, articles on our webpage, like Qdrant.tech.
Yep.
Uh, yeah, and this more technical details about our index structure is unfortunately undocumented yet. It's like it's just open source and some
Yep.
commentary
Yep.
over there, but yeah, we are, we are not yet able to like make
Yeah.
everything an article.
Makes sense. Makes sense. Cool. This is awesome. Thank you so much for taking the time. We're about at the end of the hour here, so unfortunately we got to drop. But this is fascinating stuff. I think vector databases are going to be powering a lot of the AI related search and information retrieval applications that we're going to see pop up in the next year. And it seems like Quadrant has kind of like a unique position in the market here. Yeah, someone just said awesome approach in your architecture. Now I see why Quadrant is the fastest out there. All right, so you got one endorsement. That's awesome.
Yeah, thank you.
Cool. Any kind of like final thoughts? Like if folks want to try out Quadrant, what's the best way for them to get started?
Well, for us, the best way if you go to our cloud and create free tier in our cloud is
Cool.
yeah, it's the easiest way. You don't need to even install Docker. If you're an open source uh, like advocate, then yeah, please feel free to download Docker image and run it. It's also pretty simple. Uh,
Yep.
if you are a Rust enthusiast, then yeah, you can build it from source.
Nice.
Also possible. Yeah, we have a tutorial again on our webpage. It's called. Uh, yeah, I can show you. I guess. So yeah, it's called Neural Search Tutorial. It's basically how to build a very simple application using Quadrant, some Python fast API, and BERT embeddings.
Yep.
Yeah, so you have your own. You can use any data, of course, you want.
Awesome.
Doesn't require any training. So you start with ready-made encoders and build. You can build your own code search during the evening. So
Awesome. Andre, this is fantastic. Thank you so much
Thank you.
for sharing all this. This is really awesome. I think we're going to take a serious look at this for some of Sourcegraph's backend. This is amazing technology, and thanks for taking the time to explain it to us.
Thank you.
All right, take care,
My
everyone.
pleasure.
Thanks everyone out there for joining.